In this video, we shall discuss about some problems from the chapter relation. The first problem it is given, let A the set 1, 3, 5 and B 8, 10, 12 and a relation R is defined by x or y equal to x plus y is even, that is the order pair xy belongs to R if the sum of x and y is even. Then we have to show that R is a void relation from A to B. Now, what we know, what is a relation? A relation is, there is this R will be subset of A cross B. Then what is A cross B? A cross B equal to these order pairs will be the elements of A cross B. Now you see, in all these order pair, the first number is odd, that belongs to the first set A, and the second number, that is even, that belongs to the second set B. Okay. Now what we know, sum of a odd and a even, it is always a odd number. So ultimately the sum of these two number is not a even number. So there will be no such element which belongs to the relation R. So ultimately R is 5, that is a void relation or empty relation. Next, an equivalence relation R in A divides it into equivalence classes A1, A2, A3. What is the value of A1 union A2 union A3 and what is the value of A1 intersection A2 intersection A3. Now we have to understand this equivalence class of a set. What is a equivalence class or a partition of a set? Now you see, if this is the set A, okay, then the partition or equivalence class means we are going to partition of this set A. There are 5 partitions, you see, such that the union of all these partitions is equal to set A and the intersection of these two is 5. That means there is no common element in any of these two partitions, that is they are mutually exclusive. Okay. So A1 intersection A2 intersection A3 intersection A4 intersection A5, that is equal to A and their intersection is equal to 5. So here also A1 union A2 union A3 is equal to the given set A and the intersection of A1 intersection A2 intersection A3, that is equal to 5. Okay. This is the partition or intersection of a, partition or equivalence class of a set. Next question given, a relation R in the set S, that is 1, 2, 3 is defined by R equal to the order pair 1, 1, 2, 2, 3, 3, 1, 2. Then which element or elements to be removed from this relation R to make R an equivalence relation? Okay. What we know, what is an equivalence relation? If a relation is reflexive as well as symmetric as well as transitive, then we can say that it is an equivalence relation. Now what is a reflexive relation? For all x in the set S, if x comma x belongs to R, then we can say that the relation R is reflexive. Let us see. For 1, the element 1 of S, 1, 1 belongs to R. For 2, this 2, 2 belongs to R. And for 3, this 3, 3 belongs to R. So ultimately this R is reflexive. Now symmetricity, we have to check whether this R is symmetric relation or not. For 1, 1, the reverse of 1, 1, 1, element 1, 1 is also 1, 1. For 2, 2, the reverse of it is itself. For 3, 3 also, the reverse of 3, 3 is itself. Now for 1, 2, the reverse of 1, 2 is 2, 1, which is not in this set. So it fails to be symmetric for this element 1, 2. So, to make this R a symmetric relation, we have to remove this element 1, 2 from R. Now, we have to check transitivity. Now, if we remove that 1, 2, the relation will be 1, 1, 2, 2 and 3, 3. Now, for the element 1, 1, what is transitivity? A transitive relation. What are transitive relation? If xy belongs to R and yz belongs to R, ultimately imply that xz must belongs to R. Then we can say that it is transitive. That means 1, 1 belongs to R and 1, 1 belongs to R. Ultimately eliminating this first element and this last element, it will be also 1, 1, which is belongs to R. So, R is transitive. Same for 2, 2 and 3, 3. So, ultimately we have to remove only this element 1, 2 to make R an equivalence relation. Next problem, a relation R is defined on Z, that is set of integers is defined by R equal to order pair xy such that x and y belongs to Z, that is x and y are integers and x minus y is an even number. Then we have to show that R is an equivalence relation on Z. That means we have to check the reflexivity, symmetry and transitivity of R on Z. So, for all integers, for all, this is the symbol of for all. For all, that means for every integer x minus x, that is equal to 0. 0 is an even number. So, ultimately the order pair x comma x belongs to R, that is R is reflexive on Z. Now, symmetry, if xy belongs to R, that means for two integers x and y, if xy belongs to R, that means x minus y is even. Now, if x minus y is even, then y minus x, it is also an even number. So, ultimately y comma x, the order pair yx is also belongs to R, that is R is symmetric. Now, transitivity, xy belongs to R and yz belongs to R, that means x minus y is even and y minus z is also even. Then ultimately the sum of two even numbers is also an even number, that is x minus y plus y minus z is also even. Plus y minus y will be eliminated, that is x minus z is also an even number. So, the order pair xz belongs to R, that is R is transitive on Z. So, as R is reflexive, symmetric and transitive, so R is an equivalence relation on Z. If the number of elements in the set A is m and the number of elements in the set B is n, then there are 2 to the power mn different relations are possible from the set A to the set B. Similarly, the number of reflexive relations on a non-empty set A having n elements, that is 2 to the power n square minus n. That is, if there are 3 elements in a set, then how many reflexive relations are possible on it? That is 2 to the power 3 square minus 3, that is 2 to the power 6 different reflexive relations are possible on a non-empty set having 3 elements.